Hello everyone and welcome to our presentation today. My name is Paul Arsov and I'm the founder of the Decentralized Web project. We're building um, multiple projects and I'm going to mention them in the end of this presentation. But without delay, go back to the presentation, and it is going to be part 2 of the presentation about the current failures of AI and the way to solve them. In the previous week, we ended the presentation with analyzing what skills are and the three-way, like there's some kind of a tug of war between these definitions. The first one is the reality that skills are aggregates of unique individual behaviors. Like, for example, you must individually learn how to carry boxes of specific shapes and do so in the immediate moment. The second one is skills are transferable trends in behavior. Like, for example, you can transfer a learned routine for carrying one box to another box, if doing so is appropriate or useful. And the third skill, interpreting skills as general concepts. Like, for example, you may discuss how a person is generally good at carrying boxes, regardless of their size and shape. These three ways of interpreting skills often get confused for one another, which leads to equally confused theories of skill acquisition. Now that they are in front of us, however, we can bring them together to create a schema of how skills or all skills are formed. We start naturally at the deep end, dealing with specific situations. From there, we can work upwards to skills at coordinated systems of learning. Life must be dealt with in the moment. What causes us to pay attention, to engage, and to learn is immediate, specific, and always triggered by perceived need. When we first start to build up any skill, we are responding to a particular event which registers as one of interaction. Like, for example, solve this problem now. You don't yet know it is a skill. Categories like movie genres are generally recognized when their first instances are being created. Consider what may happen when a native pick-and-place robot encounters its first fragile object. When the item breaks, the agent will have no sense of what happened, but can only judge that it was unable to continue towards the goal which was programmed in the robot. It can perhaps guess that something about how events transpired must be tied to or must have caused its failure to satisfy the underlying motive. Going forward, the appearance of this same item on the picking palette may now trigger it to be cautious, though it knows not for what reason. because to know the reason would be to attach a useful thought to the event, and this is currently lacking. With no established path to resolve the concern, it searches for some other behavior that may lead to success. It now reaches into the storehouse of existing routines. Perhaps it discovers that moving such objects more slowly does not result in failure. This is what it would do with objects that are loosely gripped. Moving slowly allows loosely gripped items to be held at hand and thus successfully transported. At this point, it's treating the fragile object as though it were a loosely gripped one. And you and I know this is misguided, but lacking another alternative, this a fair hypothesis for the robot. It's not perfect though, it may occasionally fail. Only once it realizes that to consistently resolve the underlying issue, it must lessen the force of the grip, thus and not decrease the speed of movement. Thus, it self-corrects and creates a new routine for the item. As more situations pile up for which a delicate touch is effective, this will borrow their responses from later fragile examples, and the former loose grip ones simply because this is what works best. You can observe an equivalent process play out in language. Imagine you are watching a fellow employee reach briskly for a fragile item, one that you have previously seen shattered. As you foresee an accident and experience the accompanying anxiety or tension, you have the opportunity to take action, this time using words to avert disaster. But should you say, careful, that's fragile, or careful, that's loosely gripped? The choice of explicit linguistic category you assign to the object will be the choice of wording that you would allow the other person to treat it in the right way. You use the term that is effective. Words are no different from actions, both are merely the right response. This example demonstrates two core features of building a skill. The first is that a skill is always a reaction in a particular moment. You address some emergent situation because you foresee bad consequences. All learning is a result of an immediately perceived reason or need, even if this underlying driver is invisible to you on introspection. A lack of any such motive only results in a complacency and idleness. Its presence, on the other hand, triggers caution or attention and carves out a temporary workspace to address it with its own concepts and reasoning. Compare this to reinforcement learning, where actions are constantly being taken with no immediate propelling motive except that the agent must optimize global loss function. Every response you learn because the status quo, the existing response, proved ineffectual. Without that catalyst, your mind falls back to some prior default, since you have no reason to distinguish this situation and act differently from another. The ultimate default response is no response at all. If the default works, you continue to do it. If it doesn't, for example, if the underlying need is not satisfied, then a new, more targeted routine must be searched for on the spot. As you discover new responses for new situations, they build on top of one another as incrementally fine-tuned ways of dealing with emergent experiences, like sedimentary layers. Later acquisitions supersede former ones. Being responsive to an immediate tension also means that you don't wait for a regression event down the line, as it is in reinforcement learning, and hope you do better next time, since by then you will not be in the same situation anymore, and you have lost the opportunity to discover a better response. You experiment both in thought and in reality, and don't let up the effort until you find a resolution. The path you ultimately decide on, the one that resolves the issue, is one you record as the appropriate response. Everything else is discarded. Ideally, the behavior you learn helps consistently avoid the tension in the future, at which point it becomes an unconscious habit. This is adaptability. The range of time between recognizing a tension and the appearance of its resolution splits the agent's time into chunks of learning. The learned behavior is self-contained. It achieves a specific end, and it can be removed wholesale if needed. As discussed in the previous post, the only way to split up a stream of fluid experiences into chunks is through signals that are timed and targeted to an immediate need. Have we encountered the second aspect of learning, a new skill, the separation of concerns? The individual granular units of learned responses are separate, distinct routines that can be transferred from one situation to another. Like a usable phrase, like for example this rap, you may find many situations in which it is applicable. The segregations of responses also prevents any interference between what is learned at various times. This is an oversight that currently limits the complexity of what can be trained via machine learning. Most of the instability inherent in training machine learning models can be traced to indiscriminately blending all learning into one large pot, exploding and vanishing gradients, catastrophic forgetting, and other failure to converge are all caused by the cumulative errors of repeatedly adjusting the whole model. when only one part needs to be involved in a specific situation. But to know which part, you must segregate the model into sections beforehand. Consider how failure scenarios are addressed in supervised training models, like behavioral cloning. When you discover a failure case, you retrain the whole model with additional samples that account for that scenario and indicate the right answer. You adjust the entire network to accommodate the new lesson. From the inside, the model's point of view, the new case is in no way distinct from the others it has learned. But from the outside, from the trainer's perspective, the exceptional case was distinguished by the motives that drove it. There was a particular set of experiences that triggered you to pay attention there and then, and a particular problem underneath those. By treating all behaviors as homogeneous, the AI is deprived of this extra information. The relation between what was learned and the motive that caused it is missing. To give the behavior meaning, the model must maintain a record over time of the causes of what it has learned. It would be equally incorrect, however, to attempt to introduce this information explicitly. When we, like the developers, try to describe and address the issues in the long tail, we intuitively split them into what we perceive to be the correct problem categories. Like, for example, this was a multi-pick and this was an empty grasp. These divisions are artificial inventions and may not faithfully represent how we actually deal with the situation, where we to enforce these explicit categories into the behavior of a robot through custom code or accessory models, all the underlying nuance and flexibility would be erased, and the organic boundaries of learning would disappear. As the authors of this so-called rupture, we must now become the caretaker of that separation as well. We are constantly on call to fix them whenever they fall. The artificial intelligence abrogates our responsibility for maintaining a division that it was forced into accepting. This was why connectionists' approach originally gave up the discrete logic of good old-fashioned AI, out of fear of imposing too many of our poorly informed opinions on what the agent does. They preferred the AI learn to differentiate these cases on its own, without a trainer enforcing it through custom code or corrective training. In doing so, they went too far into the opposite direction, merging all learning into one giant function. They left the question of what kind of structure would form within the black box of the learned neural networks to winds of fate. Transformer architecture um, Transformers architectures are starting to reintroduce separation of concerns through the method of attention, and this has been relatively successful. What is still missing, however, is the separation of motives. These later comprise the skill domains. Much of what is written may sound like common practice when designing reinforcement learning agents. RL also begin with a set of basic rewards out of which the agent builds its own intrinsic values about the world, so-called Q values, and Q values may be seen as analogous to sub-motivation. For example, a robot may place a low value on having a loose grip on an item since it has learned that doing so is often on the path to dropping the package. And Q values also preempt the higher level issues by preceding them in time. However, the space of learning in the reinforcing learning agent value model is homogeneous. The presence of low value situations such as grabbing a box and covering its barcode does not trigger a sub-problem routine. That is a recognition of an emergent concern with its own discrete domain that must be resolved on its own terms. No focused experimentation is possible that could give rise to domains of skill. RL systems are always regressing towards a global reward. In a giant problem space, there is also no way to connect the learned value or behavior to the parent value or state that created it. If you ever want to investigate why the robot decide to pick objects from the left side, you cannot trace the cause to, say, that time when it dropped an imbalanced item, that information is lost, deemed unimportant. All values are presumed to be caused by the main rewards, and there's only ever one task. In order to resolve this issue, value states must be treated as hierarchies of distinct entities, each triggered by a concrete set of sensory inputs, where parent motives generate child motives and responses. That way, the destruction of a parent, the sudden recognition of the delusive nature of a particular value, can delete all its children, including values, thoughts, and actions. This allows the mind to create domains of understanding. Yet to do so requires that we disentangle and separately catalog each piece of learning, each thought, each action chain. As you can imagine, that is entirely at odds with the fundamentals of deep learning networks, though it is more in line with logical AI. We must therefore reconsider what the concept of neural network entails. Rather than adjusting the parameters of a large single function, we must catalog a large collection of individually transferable behaviors. Transference and generalizations are widely acknowledged to be the key to handling the problem of the long tail. In this post, we have shown how individual skills are created as a hierarchy of specific problem resolutions, and also how they can be applied to new situations on the basis of experiments proving their immediate efficacy. A catalog of skills is like an enormous tool shed with rooms for millions of entries. Every time we add a new tool, we do so for a particular reason, any particular moment, usually because none of the existing tools resolved the issue we were faced with. As new situations are discovered, new tools become necessary beyond the capabilities of the existing ones. We may sometimes find that existing tools are useful in many different situations, and so we transfer their applications from past to present ones. This may happen due to the similarity of the problem circumstances through trial and error, or else by reasoning through what the consequences of the transfer would be. Once applied, if the tool is effective, using it becomes an automatic habit. Yet, even then, the skill always carries with it the tension that draws its design. But the analogy above is imperfect. It must be amended. Unlike real tools, we cannot purchase skills ready-made from an external source, although the raw materials out of which we build them are whatever is immediately at hand. We must nevertheless make each additional tool ourselves with features that serve our current purpose. The difference is a small one, but it is critical for understanding the ontology of categories. No skill or concept exists outside of what we invent. We must build it all up anew, and piecemeal. This allows our mind to be adaptable to novel, unexpected circumstances at the expense of long educational period. The fact that our own inventions end up being similar in many ways to those in others' tool sheds is a consequence of the shared nature of the physical reality in which we both create them. That in the unity of coming into common terms with other people when working on a shared project. There's another way the tool shed analogy must be adjusted to capture the essence of skill formation. There's no separation between the owner who identifies the problem and the tool to resolve it. Whereas Real-life tools are only a solution to a problem. Every skill is simultaneously the discovery and the recognition of a problem and its solution. Those without a skill generally cannot even see the situation as a problem. In philosophical circles, we commonly tend to identify the one searching for solutions as the conscious self, the owner of the tool shed in this analogy. Yet in reality, the tool shed has no owner. It is the tools themselves that are creating one another as they recognize their own shortcomings. And with this said, I'm ending this presentation. Thank you for viewing, thank you for listening. And I'm coming back to the beginning of this presentation where I told you that my name is Paul Arsov, and I mentioned that we are working on several projects. Currently, there are 3 different projects that I want to mention. The first project is the Decentralized Web project. It is building decentralized communication and advertising platform, and the website and the URL of this project is decentralizedweb.org. Decentralized and web, they're 2 words and they're typed all together. Decentralized.org. Once again, decentralizedweb.org. The second project that I want to mention is a 3D NFT marketplace and collection of NFTs based on 3-dimensional objects. What is unique, special, and interesting about this project is that we built our own 3D software engine. It has multiple capabilities like speaking, voice recognition, basic artificial intelligence, and displaying objects in a way of stereoscopics so that you can see them in real 3 dimensions. The website and the URL of this project is 3dnft.decentralizedweb.org. 3dnft is typed in a way of the number 3 followed by the letter D followed by 3 other letters NFT, and it is all together 3dnft. Then there is dot, then there are 2 words, decentralized and web, and they're typed all together, decentralized web, then there is dot, and it ends with org. Once again, 3dnft.decentralizedweb.org. The third project that I want to mention is project about building charging products for electric vehicles and switching products for high voltages and high currents. This project is based on the assumption that the current solution for charging of electric vehicles done in the way of we call it gas station model way. It resembles the way internal combustion engines are loading fuel at gas stations, and in the same way like electric vehicles, they're coming to special locations which they have several columns. Owners of electric vehicles are connecting charging cable to their vehicle. They start charging, pay, and leave. But we estimate that ultimately is going to become insufficient to the number of these charging stations to charge electric vehicle. That's why we propose so-called parking lot model, where vehicles are going to be charged at the parking lot, either at the place of living, if the person lives in a high-rise building with a parking lot in the base, like ground floor, or with multiple underground floors, or like parking lot at the place of work, where the person is going to like come with their electric vehicle and stay during the day. With this set, I like to mention the name and the URL of the website of this project. It is power.rstack.com. Power is the ordinary word for power, then there is dot, then there something sounding like rstack, which I can spell it letter by letter. It's Alpha Robert Sierra Tom Echo Charlie Hotel, altogether rstack, and then there is dot and it ends with com. And the last project, one additional project which doesn't have yet a website, that I like to mention and that we are working on, is a project about intelligent devices. It is based on the premise that the current leading edge of technology, so-called large language models, which like are assumed to be artificial intelligence, the current leading edge technology is going to eventually transition to new direction, and new direction we estimate is going to be in the direction of robotics. And we are working on these intelligent devices, which are going to be combined into robotic devices, which are going to have vision, they're going to have speech, they're going to have motion, and they're going to have communication, and their intelligence built on sensory experiences coming from outside and collected by the individual device. We are soon going to be releasing a website of this project and samples, but like we started working very recently on this, and I like to mention that currently we are working on like vision and motion capabilities for these intelligent devices. With this said, thank you for listening, thank you for viewing. Have a nice day, have a nice evening, and goodbye.